Hello and welcome back. So this is lecture 5B, assessing the validity and reliability of diagnostic and screening tests. Just a quick reminder, we have quiz 2 next week, so it will cover chapters 4 and 5, so that's going to be lecture 4A, 4B, 5A, and 5B. I would also recommend that you go over your homework assignments and any calculations that I show you in the PowerPoints, all right? So it should be pretty straightforward, very similar to what you experienced so far, okay? All right, so let's go over our learning objectives for today. This is going to be a very dense lecture and we're going to cover some very important concepts. Today we're going to talk about how screening tests are applied in the same individuals, either by using simultaneous or sequential testing. We will introduce a new measure of validity, the predictive value. And we will further discuss reliability specific to testing and differences between reliability and validity. So let's just say you want to go to the doctor to check whether or not you have diabetes. The doctor can subject you to either sequential testing or simultaneous testing. How does she or he decide which one to use? Well, it will depend on how serious your condition might be and how important it is to get your results as soon as possible. Now we're going to examine each type a little closer and see the pros and cons of each one. So with sequential testing, right, so that means you have one test and then you have a second test after you receive the results of the first test, right? So in this case scenario, let's just say the first test comes back positive. That means you will get a call from your doctor to go back for a second test. Usually the first test is less expensive and is designed to screen a lot of people, while the second test will be more sophisticated, probably more invasive and expensive, but also it's going to be more sensitive. And I'm talking about sensitivity, right? How accurately that test will actually be able to identify you as being positive. Meaning if you're truly positive, you will get a positive test as well as minimize the chance of getting a false positive results in case you are not. Let's see an example to understand how sequential testing works and how it affects the validity and reliability of a test. In this example, we will assume a hypothetical population of 10,000 people. And we're going to let's just say that we measured and we know that the prevalence of diabetes is 5%. That means that 500 people are actually diabetic and 9,500 people, they're actually free of diabetes. If we set the sensitivity of the test at 70%, that means that it will correctly identify 350 people of the 500 people who have diabetes. So 70% of 500 people. You can see the 350 inside the true positive cell. With a specificity set at 80%, we will correctly identify 7,600 people who do not have diabetes. So that's 80% of 9,500 people, right? So 7,600 people will test negative. Now let's look at this 2x2 table and other positives for diabetes. Okay, we will do the math. And we will see, so 500 people truly have diabetes. We were able to diagnose 350 of them. That means we still have 150 people who are actually positive for diabetes, but they tested negative. Likewise, 9,500 people we know from the prevalence data, right, truly do not have diabetes, but our test was able to correctly identify 7,600 of them as negative. That means we are left with 1,900 people who tested positive. Okay, so these are false positives. Okay, now if we add up the total of our positive test results, we see that we have 2,250 people who are positive for diabetes. At least with this first test, 2,250 people tested positive. That means all these people need to be brought back for more testing. So the 2,250 people who are brought back for the second test, now we have to actually subject them in a test that it's going to be a little bit more sensitive and more specific And such test is going to be, for example, a glucose tolerance test. Now, let's see what happens to sensitivity and specificity, right, when we actually increase them with the second test. So we brought back all these people for testing, right? So the specificity and sensitivity now is set at 90%, which essentially means 90% of the 350 people who tested positive in the first round, right? Now we're going to get 315 out of the 350 to test positive. That also means that we have 35 people who will test negative, although they are actually positive. Likewise, 90% specificity of the 1,900 people who are brought back, right? These are actually, we're going to get now this time around 1,710 people to test negative, but we're still going to get 190 people who are going to test positive, and they're actually negative. So let's examine now. Let's see how the two tests, what is our net sensitivity and net specificity between those two. Out of the 500 people who have diabetes in the community, we were able to identify 315 to test positive after the second blood test. That means 315 out of the 350, that is a 63% net sensitivity. Thus, there is a loss in sensitivity by using both tests. For net specificity, we have correctly identified 1,710 people who do not have diabetes from the second test and 7,600 from the first. Thus, we have 7,600 people being true negatives plus the 1,710 true negatives divided by the 9,500 person who truly do not have diabetes. As we know, based on the prevalence data, that means that our net specificity is 98%. Okay? Now, with 98%, that means that we have a net gain in specificity by performing sequential testing. With simultaneous testing, you are actually running two tests at the same time. You do not wait for the first result to come in. As you probably figured it out, there are times that time is of the essence, and we need to find answers quickly, such as like being in an emergency room, right? And in order to save someone's life, you're going to run multiple tests at the same time. Now, to be considered positive, though, with simultaneous testing, a person must either test positive in the first test or in the second test or in both tests. Again, let's take a hypothetical population of 1,000 people. Let's assume that the prevalence now is 20%. That means that we're going to have 200 people who are positive. Test A, we set the sensitivity at 80% and the specificity at 60%. Thus, we're going to get 80% of 200. That means we're going to get 160 true positives. With test B, which takes place at the same time, we're going to set the sensitivity at 90% and specificity at 9% as well. And that means 90% of 200, we're going to get 180 true positives with the second test. But how do we figure out how to calculate net sensitivity, since a lot of people who tested positive for test A also tested positive for test B? So there is an overlap. And what the purple circle is showing you here is the number of people who tested positive for both tests, test A and test B. Now, with test A, there were a few people here that actually tested positive only with this test. And likewise, the blue circle, the extra side here, if you say, these are people who tested positive on the second test, but not in the first test. So only the area that overlaps, this purple area, is people who actually tested positive in both tests. So to calculate the numerator for the net sensitivity, we will take the 90% sensitivity of the second test and multiply it with the positives that the first test identifies. That's 90% of the 160 people. Okay, that is 144, which means 16 people, right here. So if we subtract that 144, we're going to see that there's 16 people who test positive only for test A. And if we do the same thing with the test B, we're going to see that we're going to subtract that 144 that we got from the 90% sensitivity set by the second test. We will subtract it from the 180 people who tested positive on test B. That means there are 36 people who tested positive only with that test B. To calculate net sensitivity for simultaneous testing, we will add up the 16 people who tested positive for the first test to the 144 people who tested positive on both tests. And then also we're going to add the 36 people who tested positive on the second test only. And then we're going to divide that by the 200, which is the total number of persons who we know are positive for the disease. Now, as you can see, your net sensitivity now is 98%. Thus, when we use simultaneous test, right, there is a net gain in sensitivity. We went from 80% that we set test A, and then test B was set to 90%. We actually increased the net sensitivity now to 98% by using both tests. However, there is a net loss of specificity compared to using either test alone. Note that I will not ask you to calculate net sensitivity and net specificity, but I do want you to understand the relationship between the two. What happens, right, when we use simultaneous tests versus sequential to the sensitivity and specificity. If you take a look inside your text on page 99, you will find the calculations for net specificity as well. But the idea here is that there's a trade-off between the two. We run two tests at the same time to find out if someone is positive, and as a result, our sensitivity goes up. Again, the bottom line is that what you need to remember is, memorize this, in sequential testing, there is a net loss in sensitivity and a net gain in specificity. In simultaneous testing, there is a net gain in sensitivity and a net loss in specificity. Now let's talk about predictive value. Up until now, we have asked the question, how good is a test at identifying people with and without the disease? Which is a very good public health consideration. In a clinical setting, however, the question that physicians would ask is, what proportion of patients are truly negative, given that they have a negative test, or vice versa? How many patients truly have the disease, given they have a positive test? Essentially here, what we're asking is how well a test predicts the result. We are looking to find the probability that the result of a test captures the true state of disease for the patient. That is called the predictive value of a test. Here's the formula for the positive predictive value, which means the proportion of patients who test positive and are actually positive. And then we also have negative predictive value. Negative predictive value is the proportion of patients who test negative and actually do not have the disease. If you haven't noticed yet, the calculation is very similar with the sensitivity and specificity calculation, so I do not want you to confuse the two. Only this time, in the denominator, we add a cross instead of actually going down. So instead of like going vertically, we're going to be going horizontally. Okay, so let's take a look at the formula so you do not confuse the two. So positive predictive value, right? So here we're talking about positive results essentially. That's why it's called positive predictive value. So it's going to be your true positives divided by your true positives again, plus the false positives multiplied by 100%. Okay, and then the negative predictive value, you're going to be going across this way. So that's going to be your true negatives divided by true negatives plus false negatives, and again, multiplied by 100. Sensitivity and specificity, as we said previously, are characteristics of the test being used. Positive predictive value is affected by two factors, which are how prevalent a disease is, and in a rare disease, what is the specificity of the test being used. To further understand this concept, you can read Table 5.8 from your book, where it compares two populations, one with a 1% disease prevalence and the other one with a 5% prevalence. If you run the calculations, you will see that the higher the prevalence, the higher the positive predictive value will be. And the higher the risk in a specific population, the higher the positive predictive value will be. So reliability of a test. Let's examine how we measure reliability in screening or diagnostic tests. As you remember from your statistics class, reliability deals with replication. How well can we replicate the results we just got? You can imagine that if you run a test 10 times and every time you obtain different results, that would be a very serious issue and you would not trust the test. To evaluate reliability in our screening tests, we need to examine different sources that could affect reliability. So based on what I just told you, we have three types of reliability: intra-subject variation, intra-observer variation, and inter-observer variation. Let's examine each one of them. So intra-subject variation, here we're talking for changes happening in a patient due to the various reasons, okay? So this is changes within the subject itself, the patient itself. So for example, you may measure your blood pressure in the morning and it's normal. You get maybe a 110/80 or 120/80. Later in the day, maybe you got stressed out or you drank too much coffee. Now you measure again your blood pressure and it's much higher. Depending when you visit the doctor, right, your readings will be very different, okay? So that would be an intra-subject variation. Intra-observer variation, okay, that means that the same doctor looks over the same results and comes up with different conclusion. Maybe the second time he took a more careful look and maybe he was able to notice something that he or she did not notice the first time around. Or maybe she's trying to determine, something that is very subjective and not exactly clear-cut. Think about an X-ray and a radiologist. Maybe he did not see like a tumor the first time. And to be honest with you, sometimes some tumors may be so small that they're going to be very hard to identify and actually decide if that person needs further screening or not. So maybe by evaluating that X-ray a little bit further, he actually changes his mind. So here you can see what a normal cancerous breast tissue, so A would be your normal non-cancerous tissues versus a cancerous tissues. Now here's enlarged, but you can imagine depending when the female goes for testing, right, the tumor does not have to be that large, so it can be a lot smaller, and you can see how challenging it can be to differentiate between the two. Inter-observer variation is probably more frequent. Now we'll have two or more people look at the same test and they do not all agree with what they see. The question is, what % of the observers agree in order for our findings to be considered reliable? Kappa statistics is a measure of reliability. It answers the questions: to what extent does the agreement between two observers exceed the level of agreement that would result from just chance alone? Your book shows you how to calculate kappa statistics, but we will not cover this in this class. You only need to know what the measure is and how to interpret the findings. The basic concept is to divide the number of agreements that you have with the perfect number of agreements. For example, if you have 5 observers agree on a test results out of 6 who actually took a look at it, that means your kappa would be 5 out of 6, or 0.83. Is that good? This is how you interpret your kappa statistics. So values, the values will range from 0 to 1. So a kappa statistic that is greater than 0.75 is absolutely excellent, okay? So this is probably what we should be aiming for. A kappa between 0.4 or 0.75 is a good agreement, not great, but good. Anything below 0.4 is honestly unacceptable or extremely poor. The bottom line is that we want a test to be both reliable and valid. Although there is a possibility to have a non-reliable valid test, if we cannot replicate the results, essentially it is useless. So that is it. Have a good one, everybody, and I'll see you next week. Take care.